Welcome to another podcast. This episode, we're going to be taking a look at how to form and complete truth tables for these basic, what are called Boolean operators. I want to start with sort of a description of what the operators we're going to look at are, and then we'll look at their truth tables. So the first operator is, it looks like a little tilde. It stands for not, or it's the negation operator. The next one is the wedge, which stands for and. And then the V operator, which is or. So these are logical operators. We've got the forward arrow, which stands for implies, but it's called the conditional. So this is the conditional operator. And then it can go in either direction. Then if we have a double-sided arrow, this is referred to as the biconditional. And so these are the basic Boolean operators that we're going to take a look at in this video. A truth table is a table that looks at all possible truth values of a given statement depending on the operations used. And so I'm going to start with just a simple explanation of what the negation operator does. So the negation operator looks at P and then changes the truth value for not P. So for example here, if P were true, then the negation of P is false. If P is false, then the negation of P is true. So that makes pretty good sense in terms of what that operation is doing. It's just changing the truth values. So the P that we start with here is called the predicate statement. Obviously, it represents some sort of words. If you looked at the previous video, we diagrammed parts of the statement of a theorem before we proved it. So P refers to a statement being made in something like a theorem. So if the statement is true, then the negation of the statement is false. And that's basically what we're doing with these arguments. Next up is we're going to take a look at and. So let me build a table for that. So and is a compound or binary operation in that it takes two arguments. The negation doesn't. The negation only involves one predicate. But because and is binary, I need two predicates, P and Q. And then I basically start off the truth table by listing every possible combination of truth values. They could both be true, one could be false, the other could be false, or they could both be false. So this is every possible combination of the truth values, and then what we do to complete the truth table is look at what the AND operator does in each case. So if both statements are true, then the statement overall is true. If one is true and the other is false, then the statement as a whole is false. Similarly, it's false here, and it's definitely false there. So the AND operator is only true in case both of the preceding predicates are true. All right, let's move on to OR. OR is next. So OR is also a binary operator. So we're going to need two predicates, all possible truth values, and then let's look at P or Q. So true or true. Basically, the way that the OR operator works is the statement's true if at least one of the arguments is true. So true or false is true, false or true is true. These are all true. The only one which is false is if both statements are false. All right. Next up is the conditional. So the conditional is a binary operator as well. The conditional is what we think of when we think of an if-then statement. And so we're going to look at what are the truth values for an if-then statement. So P implies Q. That's how you can see it written sometimes. You'll oftentimes hear me say implies. So P implies Q, this operation. The way that this operation works is if you say it's true and it implies that Q is true, then the statement is true. If you say P implies Q and P is true, but that doesn't end up happening that Q is true, then the statement that you've made is a false, because clearly P happened, but it didn't imply Q because Q didn't happen. Finally, these last two are sort of weird to talk about here, but they're both true. And they're both true because the initial statement was false. If you read through the text, and we've kind of talked about this a little bit in class, these are what are called vacuously true. So if you ever hear anybody talk about vacuously true, they're talking about the conditional in the case where the first predicate or the first part of the statement happens to be false. All right, in terms of the biconditional, so the biconditional is a binary operation as well. So P if and only if Q, so this is the if and only if operator. Once again, list all possible truth values. And the way that the biconditional works is we're going to show in another video that this is logically equivalent to P implies Q and Q implies P. In other words, and the proof bears that out. Remember, the way we proved if and only if statement is we proved both directions. So thinking about this, true implies true, then going in both directions, true implies true and true implies true, you get true on both parts. So as a statement, this is true. Then this is the one that's tricky because true implies false. Going in the forward direction, you don't have anything. It's false. So this statement's false going in one of the two directions. This one is fine going in the direction of P to Q, but going in the direction of Q to P, you've got T to F, and T to F is false when I look back over here at the conditional. So this is a false statement. And then finally, false in both directions is vacuously true in both directions. Therefore, the biconditional would say that it's true. A couple other little pieces of terminology that we need to know. Some statements, some logical statements in which all have true values are called tautologies. So if you have a logical statement that's made in which every truth value is true, then that statement is a tautology. The primary example of a tautology that we'll run into sometimes this semester, but usually these are not intrinsically valuable. But the easiest example of a tautology is P implies P. So if it's true in both directions, then it's true, because true implies true. If it's P implies P, true, true, true. And then if P is false, then it's false implies false, which is vacuously true. So you can see here that because all of these truth values are true, then that says that P implies P is a tautology. The opposite of that is if you look at a logical statement and all of the statements are all false, then that logical statement is called a contradiction. It's a statement which is made which can never be true under any circumstance. And so the basic contradiction, or the most appropriate contradiction, is P and not P. So let's go ahead and write that one in. So basically it's like this. If you do P and not P, then we know how the negation works. But then if I ask P and not P, in other words, both to simultaneously exist, that can't happen. And you see, in fact, that it's false in both cases. So if all the values are false, then that leads to a contradiction, and the easiest contradiction to talk about is P and not P. That is a contradictory statement. In fact, we'll use contradictions to our benefit to help prove some things later in the semester. So this is supposed to be a soft introduction to the idea of predicate calculus or logical calculus, involving truth values, diagramming sentences, understanding their structures. It's important that you know for these basic operations what the truth tables are off the top of your head, so you don't have to rederive these each time. All right, thank you for watching.